Welcome to Conceptual Physics at Delaware Tech, Chapter 11, Atomic Nature of Matter. So in this unit, we're going to talk about the atomic hypothesis, the hypothesis that matter is composed of atoms. We'll talk about the characteristics of atoms. We'll talk about atomic imagery. That means pictures of atoms. And we'll talk about the atomic structure, a little bit about the history of what people thought was the structure of the atom. We'll talk about the elements of the periodic table, and we'll talk briefly about the relative sizes of atoms and how they get bigger or smaller depending on where they are in the periodic table. We'll talk about isotopes. These are types of atoms of the same element, but they have different weights. Then we'll talk about how atoms combine with different types of atoms, different elements to make compounds, and how compounds come together to make mixtures. We'll talk about what molecules are. Molecules are a combination of atoms that are either the same or different atoms. And we'll talk about antimatter and some relatively new concepts, dark matter and dark energy. So here's a quote from Richard Feynman. Richard Feynman was a brilliant physicist who got the Nobel Prize in 1965. He was involved in the Manhattan Project in the 1940s. As a young man, and later got the Nobel Prize for studying the relationship of light and matter with quantum mechanics and reconciling it with Einstein's theories of relativity. So all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are at a little distance apart, but repelling each other when they are squeezed into one another. And this is true. Atoms will frequently be attracted, but if they come too close, they will push off from one another. So the idea of matter and what matter is composed of goes back a long ways, over 400 years BCE. The first recorded mention of the components of matter, what we now call atoms, was from Democritus and somebody who is reputed to be his teacher, Lycopus, though some people argue if Lycopus actually even existed. But Democritus definitely did, and Democritus figured that all matter was composed of these indivisible particles that if you took a rock and you cut it up into pieces and you cut that into smaller and smaller pieces, you kept going. Eventually you would get to little tiny pieces of rock, little tiny stones that look like your original, but they can't be cut anymore. And in fact, the word atom comes from the Greek word atomos. A in the atomos means not or can't be. And tomos, as in anatomy or microtome, means to cut. So the word atom literally means can't be cut. In other words, you can't go down any smaller. Now, we know we can go to subatomic particles, but for a long time, we didn't know that we could even do that. And he thought the same thing about stone, about furs, about anything he was looking at. And then just a little while later, Aristotle had a totally different vision of how all matter is put together. He thought that matter was composed of four basic elements of what he found around his universe: fire, earth, air, and water. And various combinations, because each of these four elements, the Aristotle elements of matter, had different properties like dry or hot or wet or cold, depending on what substance it was. It was some combination of these four. Now we know obviously that matter is not composed of this, but for a long time, for almost 2,000 years, this was the prevailing idea of what matter was. And by the 1600s, people were making more serious inquiries about the structure of matter, maybe even early as the 14 and 1500s. But by early 1800s, John Dalton, who was a school teacher, but he was other things, he was a chemist, a physicist, meteorologist, he took all these different ideas that he had learned about matter and what we thought were atoms at the time, and put them together into his rules of structuring what atoms must be like. And most of his rules are mostly correct to this day. And so that's represented by that reddish orange ball at the top here. Dalton's model was just that atoms were solid balls of whatever. And later on, other scientists realized, oh, well, these balls have positive and negative charges inside of them. And then that was Thomson who discovered the electron, and then Rutherford discovered that the nucleus was not, the positive charges in an atom were not spread all over, but they were concentrated into a core that he called the nucleus. So we learned about the nucleus. And then Bohr, Niels Bohr, a Danish physicist, he realized that the electrons must be in what he thought were orbits around the nucleus. So you have these negatively charged electrons around a positively charged nucleus. And then shortly after that, Bohr, along with other people, led by Schrödinger and Heisenberg and over a dozen other physicists, but Bohr was actually part of destroying his own model in 1926, and that's when they realized that the electrons are really in little pockets of space, of volumes that are essentially mathematically defined volumes of space where all the electrons in an atom would reside most of the time. And that's the modern view of an atom, what we call the orbital model of the atom. We'll just mention that briefly. So in 1827, Robert Brown, who was a Scottish botanist, he was studying plants, and in particular, he was studying pollen particles in a microscope, as well as soot and dust, and along with water. Now, he couldn't see the particles of water. Those are molecules. They're far too small to see with visible light, like almost all molecules are. But he could see the pollen particles, and he saw them moving in what he thought were random motions. And we now call that motion, we name it after him, it's called Brownian motion. And a little while later, Einstein was thinking about that and how it related to the water molecules and all molecules, and realized that this might be some early evidence that there really are atoms, that they're not just theoretical about what people had been thinking about what matter was made of, that there was real evidence that there must be these very, very tiny particles, possibly that couldn't be seen, that are in fact the atoms or molecules making up the bulk of matter on Earth. So we now know a bit more about the atom. We know the components of the atom, and this diagram is really Niels Bohr's idea of the atom. It's Niels Bohr's model, and he thought it was these orbits around that were in different planes, spinning around the nucleus, like kind of a messed up solar system. We now know that this is not the case. This is not exactly what's going on. The electrons may go in orbits, they may go in lines, they may go in curved paths, but they stay in certain volumes called orbitals, not orbits. But we know the atoms are incredibly tiny. We know that they are 30 to 300 picometers in radius. So that's double that is in diameter, 60 to 600 picometers. A picometer is a trillionth of a meter. So this is less than 1/1000th of a meter wide, these atoms, many of them much smaller than that. So they're far too tiny to see with visible light. Visible light wavelengths are over 1,000 times bigger than these lengths. So we would never be able to see them with regular light. We have to use other methods to see atoms. And we know the atoms are composed of a nucleus with positive and neutral particles in the middle, and the electrons kind of buzzing around, forming a cloud around the nucleus. And they're in various different energy levels or different volumes of space that all have their own energy levels. So we don't call them orbits anymore. We call these volumes of space orbitals. So atoms are numerous. If you have even a small amount of matter that you can see, there are an enormous number of atoms in there. Your body has 7 times 10 to the 27 atoms. That's 7 with 27 zeros. That's how many atoms roughly are in your body. The universe has many more than that. It's 1 with 78 to 82 zeros after it. That's how many atoms are just in the observable universe. And the real universe, the total universe, may be much bigger than what we can observe. Atoms are always in motion. They're always flying around unless they're in solids. But even in solids, they're vibrating. So everything's moving. It's either Brownian motion or a random vibration, or vibration that has been put in place by some excitation energy. But they're always moving in some form or another. And what's interesting is if you took a look at how many atoms are in just a single exhaled breath from you. There are so many atoms, so many molecules coming out of your mouth when you just breathe once, that within a few years, those atoms, because of Brownian motion spreading them all through the world, this random motion of atoms bouncing against each other, molecules bouncing against each other and moving slowly and gradually, all of those atoms from your one breath will be spread around the entire planet within a few years, and everybody will get at least a piece of that. in their next breath 3 years from now. So it's kind of a weird concept that you have breathed the same air as everybody historical that you've ever thought of throughout history. Now, atoms, where did they come from? Well, hydrogen atoms were probably made very soon after the beginning of the universe. The universe started 13.8 billion years ago. We know that number very closely. It's 13.78 plus or minus a very narrow range of years. Physicists have really narrowed down the age of the universe quite well. And most of the hydrogen that was formed in the universe happened about 379,000 years after the beginning of the universe. So this is just a blink of an eye after the beginning of the universe compared to how old it is. So most of those atoms were formed right away, and then those atoms were combined over millennia by stars, pressing them together, fusing them together, make bigger and bigger atoms. Sometimes explosions were necessary to make huge atoms, like you need supernova explosions to make big atoms like uranium. But these atoms have been around for many, many, many years, long before even the Earth was in existence. So which of the following statements about an atom is false? A, atoms are smaller than the wavelength of visible light. B, atoms are mostly empty space, just as the solar system is mostly empty space. C, atoms are perpetually moving. D, atoms are manufactured in plants and in humans during pregnancy. E, all are correct. I'll let you think about that for a second. Well, the one that's false is that atoms are manufactured in plants and in humans during pregnancy. Atoms were around long before. We don't create the atoms. The atoms were created in the beginning of the universe. They were created in stars. They were created in star clusters, in star explosions. That's where the atoms are made. And then sometimes new atoms are made from radioactive decay of big atoms making new, smaller atoms that might not have been seen before. I will tell you there's one other statement in here that I would disagree with. B here says atoms are mostly empty space. And that is because the general understanding of atoms is that we have a very tiny nucleus where the protons and the neutrons are located, and the electrons are just kind of flying around in this huge volume of space that makes up the bulk of the space of the atom. But that's not exactly correct. Modern physicists don't look at it this way, and it's fine if you do. I don't test on this because I think this is a subtle point, but the fact is that volume of space is the collection of electrons. The electrons are not real, they're really infinitely small points in space that are everywhere at the same time within that volume. So physicists like to think of electrons as mathematical functions that say this volume is where I'll find the electrons most of the time. So I will call this volume of space, these orbitals, these volumes, those will be, either occupied by electrons or not occupied by electrons, but that volume essentially is the electrons. That is where they are residing all at once within the volume. So it's not really empty space the way you'd normally think about it. So as far as A, the wavelengths are much bigger than atoms. This is true. So visible wavelengths are between 400 and 700 nanometers. That's 400 and 700 billionths of a meter. So very tiny, but still over 1,000 times wider than the biggest atoms, which are about 500 or 600 picometers. So they're much, much bigger. And as a result, we can't use visible light. It won't interact with atoms because it's too big to interact with atoms. The wavelengths have to be roughly the same size as whatever they interact with. So visible light is just too long a wavelength to match up to the size of an atom. And that's why we can't see atoms with even the best optical microscopes. We can think of the electron cloud in a couple ways. So this is what I was just saying about the electron cloud. One is to say that it's mostly empty space with electrons flying around, though physicists tend to view the volume of space as a probability function of having the electrons somewhere in that volume. And as far as them moving, perpetual motion, yes, they're always in motion. Unless atoms and molecules are down to absolute zero, frozen solid in place, they'll have some motion, including vibrational motion. Solids, the solids don't have many moving atoms, but they are vibrating atoms within the solid. And I will tell you, we know theoretically that it is absolutely impossible to reach exactly absolute zero temperature. In other words, no heat involved. We can get very close. People have gotten incredibly close, less than 1/1000th of a degree away, but you will never be able to get right there because it is theoretically impossible. All right, so viewing atoms, we already talked. They're too small to be seen with visible wavelengths of light. The wavelengths are just too big to match up to the tiny atoms. However, people have used other forms of microscopes to look at it. There's a microscope technology that was invented many decades ago called the electron microscope. And scanning electron microscopes can look at structures that are much smaller than visible light can be used, including looking at big atoms. So this is a picture. Each of these dots represents a thorium atom. Thorium is a pretty big element on the periodic table. I believe it's number 90. And here are some images using a scanning tunneling microscope. This was invented a little bit later. I believe a Nobel Prize was given for this technology. And shown in this picture, each of these bumps forming this ring are actually iron atoms that were placed on this. And in fact, this microscope not only can detect where an atom is by looking for interactions of electrostatic repulsion or attraction. It actually has a little tiny needle that's 1 atom thick at the tip, and it's basically coming around and looking for electrical conductance between whatever's sitting on your surface. And there were these atoms, and this tunneling microscope can actually be used to pick up individual atoms and move them in place. And I suspect that this circle was actually created by the tunneling microscope as well as being imaged by the scanning tunneling microscope. So classical model of the atom is with the nucleus at the center surrounded by electrons, and that's the way we'll think about it for now. So the modern view of the atom, we know that the nucleus is in the center. We've known that since Rutherford's days in the early 1900s. And the nucleus occupies an incredibly tiny fraction of the atom. If you had a giant football stadium and that was the size of the atom, the size of the nucleus would be about the size of a marble sitting in the giant football stadium, to give you an idea of the ratio of volume of the nucleus to the whole atom. But the nucleus is where you find the protons and the neutrons. And the protons and the neutrons have almost all the mass of the atom. So most of the mass is concentrated in this tiny point in the center. But most of the volume is from this electron cloud, this kind of mist of electron moving around so fast, many electrons or 1 electron, depending on how many it is, that fill this volume all the time, that we refer to this combination of all the orbitals as the electron cloud. So the electron cloud has almost none of the mass of the molecule, very tiny amount, about 1/2000th of the mass of the atom. But it has almost all of the volume of the atom, whereas the nucleus, it's the other way around. And we break up this volume into these specific parts of the volumes where different electrons can reside most of the time. And we call these volumes orbitals. They named it after orbits. They're not orbits. They're not going around a circle. They're volumes of space that they just equated to the old word orbits. So the cloud is really a probability function, and it is essentially the electrons themselves. Now let's talk about the components of the atom. We have protons, we have neutrons, and electrons. They're symbolized with the first letter, P, N, and E. And protons are positively charged, electrons are negatively charged. And this will be important, especially later when we get to electrostatics in chapter 22. Neutrons, as the name suggests, are neutral. They have 0 charge. The 2 particles, proton and neutron, the positive and the neutral, are the particles, found in the nucleus. They're in the center, in that little dot in the middle. The electrons are much smaller. They're much less massive. The protons and the neutrons are each almost 2,000 times heavier than the electron. But they're all concentrated in the nucleus, whereas the electrons, with almost no mass, they're spread out. So you have this very odd situation for the atom, but this is what we understand the structure is. And we've understood this pretty well since 1926, almost unchanged. So it's not really empty space, but you'll hear people say, oh, it's mostly empty space. That's not exactly correct. All right. So the atomic nucleus, let's just focus on the nucleus itself. This is where almost all the mass is, a tiny fraction of the whole volume, a few quadrillionths of the entire volume, maybe a little bit bigger than that. And the nucleus has the two types of particles which we call nucleons, the protons and the neutrons. So the neutrons are the uncharged ones, the protons are the positively charged particles. Neutrons won't repel or attract anything due to their charge. They have other interactions we're not going to talk about in this course called strong nuclear interactions with the protons. That's what holds them together in the nucleus. But the neutrons are uncharged, so they don't repel other charges, they don't attract other charges. Whereas protons are positively charged, they'll repel other protons, they will attract electrons that are oppositely charged. Positive and negative attract, positive and positive repel, negative and negative repel. So opposite charges attract, like charges repel. And you'll see this when we get to magnetic poles as well. Like poles repel, opposite poles will attract, north and south pole. All right. So quarks, you might have heard the term quark. Quark are particles that the neutrons and the protons, that is the two nucleons, are actually made from. There are a number of different kinds of quarks, and all of the major categories of quarks have been discovered. There are 6 main kinds of quarks, and combinations of three quarks will make up the protons, and combinations of 3 other quarks will make the neutrons. The quarks have weird names. They're called up, down, bottom, top, charm, and strange. And you don't have to know that. I'm just telling you, if you take 2 ups and 1 down, you make a proton. You take 2 downs and 1 up, you make a neutron. And then the other things are used for other kinds of particles. So atoms, when we say atoms, we're referring to the particles that make up most of the normal matter that you see around you, the normal substances. Neutral atoms are when we say the term atom, technically we mean that it's neutral. That means there's no net charge on it. All the positives cancel all the negatives, meaning there must be exactly the same number of protons with a positive charge in the nucleus as there are electrons with a negative charge buzzing around the nucleus in the cloud. So neutral atom, or if I just say atom, assume it's neutral unless I say something different. Now, atoms are what make up elements. You've probably heard the term elements, and some people use these terms synonymously. Elements are composed of one kind of atom. So if I said I had the element hydrogen, it's made up of only hydrogen atoms. As it turns out, the normal form of hydrogen is H2, shown in this list of examples. The normal form of oxygen has 2 atoms of oxygen, so it's called O2. Nitrogen has 2 atoms of nitrogen linked together in one molecule, so that's nitrogen gas, N2. They're not all gases. I2, iodine, has 2 atoms of iodine. That's a solid. But iodine, the elemental iodine, is just made of iodine atoms, 2 of them linked together. Some elements just are 1 atom at a time. Most of the metals are almost all like that. Iron, calcium, sodium, all the metals are like that. And all the what we call noble gases, what we used to call inert gases, like helium, neon, argon, krypton, radon, xenon, those are all single atom elements. So if you found them as elements in nature, they would be composed of individual atoms of one type. So that's an element. An element is made of only one kind of atom. Whether it's made of more than 1 atom or not is not important. It's that it's made of only one kind of atom, one element of one box on the periodic table that we'll get to. So the lightest of the elements is hydrogen. That's number 1 on the periodic table, and we'll talk about that in a second. There are 118 elements that are currently known. 94 to 98 of those appeared in nature all by themselves. The reason why there's a discrepancy between 94 and 98 is 4 to 8 of these are in such tiny trace levels throughout the Earth that it's unclear whether people call them naturally occurring or not. But there are 118 elements. The last 6 were just discovered between 1996 and 2009. We say discovered. They were actually created in giant particle accelerator laboratories with many, many physicists involved. They weren't just found in nature. They were found after bombarding huge particles together to make even bigger particles. There are a number of elements that are, the rest of the elements on the periodic table were either man-made or they were made from decays of very big elements over time. So atoms make up elements, not the other way around. So the periodic table, you've probably all seen a periodic table. I've got one on the next slide. It's a chart that basically arranges the atoms in terms of a couple things, but the number one thing they arranges in is something we call atomic number. An atomic number is just the number of protons in the nucleus of the atom. And in other words, how many protons that atom has. It is the only thing that determines what element an atom is. The number of protons, which is the atomic number, is the only thing that says what the atom is. If I said I have an atom with 6 protons, that's an atomic number of 6. That can only be carbon. It doesn't matter how many electrons. It doesn't matter how many neutrons. If it has 6 protons, it is always, always, always carbon. If it has 1 proton, it's number 1 on the table. It's hydrogen. If it's had 92 protons, it is always uranium. Protons are the only thing, the atomic number, the only thing that determines what element that atom is. The periodic table is arranged left to right, so you read it left to right, but it also moves top to bottom. Okay, so you read it like a book, left to right. If you're reading in English, it's left to right and top to bottom. And every time you go to a new box, that new box is an element that has 1 more proton. Now, because these are all neutral atoms, it also has 1 more electron to balance the charge. They always extra proton and electron. It doesn't say anything about the number of neutrons, and the number of neutrons in atoms of the same element can vary, and we'll talk about that in a second. So the atom, as it turns out, the atoms in that far right column on the periodic table, those are called the noble gases. They used to be called the inert gases because they didn't react with anything until a scientist who ended up at Berkeley, California, named Neil Bartlett, was able to make a compound with xenon, one of the noble gases. He did it by reacting platinum fluoride compound with it, and was able to make an actual molecule with a noble gas, with an inert gas. So they couldn't call them inert gases after 1962 anymore. So they're called noble gases. They're a higher order of gas. They're very, very stable all by themselves. It's extremely difficult to make compounds with them. Most of the compounds are incredibly unstable and even explosive. All right, but those compounds are so stable because their various volumes of electrons, those orbitals, are all filled with all the electrons they can have for that level around the nucleus of the atom. So you have these different orbitals, these different shells of electrons. I try to avoid the word shell. That's an antiquated term. But volumes of electrons around it, if you filled that volume up with all the electrons it can hold, it is in its most stable electron configuration, and those are called noble gases, and that's why they're so stable. So the number of electrons that are in the outer shell really is a major driving factor for how it will chemically react with other atoms. Since the noble gases are totally filled, they're very hard to react with anything else. But if they're not filled, which is all the other atoms, they tend to react with a lot of different other atoms in chemical reactions. So here's the periodic table. And I've used the periodic table that shows the actual names of all 118. And you would read it top to bottom, left to right, starting at the upper left-hand corner with hydrogen, number 1. All the way over, you go helium, number 2. And then you go to the next row, lithium, beryllium, and then you got boron, carbon, nitrogen, oxygen, fluorine, neon. I'm not going to read all of these, but you're reading left to right until you get to number 57, and you'll see there's a little break. And number 57, you have to shove that row that's on the bottom there called lanthanides into that space. And the reason why we don't do that is because nobody wanted to make a periodic table with a piece of paper that's this wide. So when these elements down at the bottom were discovered, they just said, okay, let's just slip them down here at the bottom instead of shoving them in and spreading out the periodic table so it's on a piece of paper that nobody wants to carry around. So if you get confused where to go, just follow the atomic numbers. You can see 55, 56, 57 in row 7 here, what we call period 7, and then it jumps down 58 through 71 in that row in the bottom, and then you jump back to 72, that's back in the main body of the periodic table. So that's how you would read it. Just follow the numbers and it will always lead you to the next element in the table. So the human body has a lot of different elements in it. And if you look at the ones that occupy the most mass in your body, those would be oxygen because you have so much water in your body, and oxygen weighs a lot more than hydrogen atoms. So having a lot of water in your body means you have a lot of oxygen atoms in your body, but most of it's in water. You also have a lot of carbon. This is making up the bulk of your proteins, of your fats, of your carbohydrates. But hydrogen is also part of it, as well as other atoms. Nitrogen is extremely important, especially in proteins. Calcium, obviously, in your bones. But your body has a lot of other elements in it. Sulfur and phosphorus, absolutely necessary. You have to have sulfur in proteins. You have to have phosphorus in your DNA and RNA. You have to have metal ions floating around in your cells and outside of your cells that help motor function and muscle function and brain function. You have a lot of other metals that are part of enzymes in your body that do chemical reactions, like iron or manganese. Manganese is necessary for synthesizing DNA. Iron is part of hemoglobin. It's not an enzyme, but it helps carry oxygen in your blood. So all of these elements are necessary. Maybe the last three, we're not quite sure, boron, silicon, vanadium. Maybe they're important, we're not positive. So, atoms. I talked about the sizes of atoms, and the pattern of the sizes may not be what you expect. As you go down in the periodic table, you're adding huge amounts of protons and electrons to it when you're going down a column in the periodic table. We call the columns groups. As you go down the group, they jump in size quite dramatically. But when you're going from left to right, they don't do what you think they do. They don't get bigger, they get smaller. And this is because of something called the effective nuclear charge. I'm not going to spend an enormous amount of time on this, but I'll show you a chart showing you the relative sizes, and it'll be more obvious when I show you the chart. But what happens is if you go down the periodic table, you get big jumps in size. They get much bigger each time you go down, adding a new whole row, because you're adding a big layer of electrons every time you go down to a new row. But when you're going across the row, you're only adding one electron and one proton each time. And it turns out the new electron is not occupying new volumes of space, it's just squeezing into the old volumes of space. But you're adding new protons, which are pulling the electrons in tighter. And this is called the effective nuclear charge. So as you go to the right in the periodic table, these extra protons are taking these volumes of electrons and squeezing them in just a little bit so that you get smaller and smaller as you go left to right, which is really counterintuitive. So here's a chart. If we look at any column, let's look at the first column, the first group. If you look at the top, columns are called groups, rows are called periods. And if we look at group 1, we have hydrogen at the top and we have Rb, that's rubidium at the bottom. And you can see there are big differences in size as you go down. And if you can do this for any column. If you go over to column 18, group 18, starting with helium, you start with tiny helium, then it gets bigger to neon, Ne, then argon, and krypton, then xenon. That's on the far right. But look at the second period, for instance. You're starting with lithium, Li, to beryllium, Be. You get smaller and smaller as you go to the right, and that is because the extra added proton is squeezing together that volume of space where all those electrons are. You're not adding new volume when you add an electron in a row. So it just gets squeezed by all those protons, pulling them in. They're attracting them in. But then you jump to a new row like sodium. Sodium is Na. So if you look at the second period and then jump to the third period, you see suddenly there's this big jump. So we start off with a certain size of lithium. It gets smaller and smaller and smaller and smaller until we get to neon, Ne over on the right. That's the second period on the right in group 18. And then suddenly, boom, we jump up to sodium, Na. And then sodium becomes magnesium when you add a proton and an electron. It gets smaller and smaller until it gets to argon. It never gets as small as the previous row, but it gets smaller, and then it jumps to the next row, row 4, period 4, starts with K. That's potassium. And suddenly, bam, it's even bigger than before, and then it gets smaller and smaller and smaller, all the way to the right, and then bam, it gets even bigger, and that's what happens. You get this zigzag effect in sizes. So the smallest element in the periodic table is actually helium, not hydrogen like you might expect it. It's in the upper right, not the upper left. But the biggest element in the periodic table is in the bottom left. Now, it's not even shown here. It's below rubidium. Cesium and francium are below that. Those are even bigger than rubidium, and those are the biggest elements in the periodic table. So ions, what are ions? Well, ions are just a charged atom. If the atom has a positive charge, +1, +5, +7. Or a negative charge, -1, -3, -5. It's always whole number charges. Always an integer number of charges. Okay, could be a zero charge. It's always a whole number, either positive, negative, zero. And if you have if you have missing electrons, in other words, your electrons are not the same as the protons in the middle, that means you're missing electrons. You have a deficiency. That means missing electrons, missing negative charges, mean you have a positively charged ion. You don't need to know this. They're called cations. If you have extra electrons, in other words, more than the number of protons, we generally don't change the number of protons in an atom unless we're doing some nuclear reaction. If we're doing a chemical reaction, we're just messing with the electrons. You either have too many or too few. And if you have too many, you have an extra negative charge because electrons are negatively charged, and therefore it will be a negatively charged ion. We call those anions. Again, you're not responsible for those names. So cations are positive, anions are negative. The positive charges are deficiency of electrons. The negative charges are excess electrons relative to the number of protons for that atom. You always have to look at how many protons that atom is. And if you know what element it is, you automatically know what its atomic number is. And if you know what atomic number it is, that is exactly the number of protons. So if your electrons are greater than the atomic number, you have extra electrons and a negative charge. If they are less than your atomic number, you're missing electrons and you have a positive charge. For example, helium has an atomic number of 2. That's 2 protons. So if it only has 1 electron, it's missing an electron. It has a charge of +1. It's missing a negative charge. And it's hard to think about dealing with negative charges. It's much easier to think about missing and adding positive charges. But unfortunately, these things were named weird, and you can thank Ben Franklin for doing that. He had to give them names, and he decided to name one positive and one negative, and it just made things harder. And you'll see this more when we get to circuits in chapter 23. Oxygen's another example. The atomic number of oxygen is 8. It has 8 protons. If an atom has 8 protons, it's oxygen. If it's oxygen, it has 8 protons. That is fixed in stone, can never be changed. The electrons can change. The neutrons can change. But the electrons, if you have more than 8, you have a negative charge. And so 10 is 2 negative charges, so it would be oxygen -2. Now isotopes, now we're changing the number of neutrons, not the electrons, not the protons. The neutrons don't have a charge, so it doesn't change charge. It just changes how heavy the atom is. So isotopes of the same element have exactly the same number of protons because that's what the same element means. They have to have the same number of protons, but they have different masses. Well, the only way to make the mass different if you can't change the number of protons is to change the number of neutrons. The protons and the neutrons are about the same mass. We'll call them 1 atomic mass unit. The neutrons are just slightly heavier than the protons, less than 1% heavier, slightly heavier, but we'll call them both a unit of 1 weight. And so a quick and dirty way of figuring out the weight of an atom without actually measuring the true weight of the atom is just to count the protons and the neutrons together, because that's where the bulk of the weight is in that atom. And so atoms of isotopes of the same element have exactly the same number of protons, but they have different numbers of neutrons. And because they have different number of neutrons, they have different numbers of protons plus neutrons, and that's their mass number. So their mass number is just the sum of the protons and neutrons, the nucleons that actually have significant mass. And it turns out atoms of different isotopes of the same element, in other words, 2 different carbon atoms, one that has 6 neutrons and one that has 7 neutrons. So carbon 12 has 6 protons and 6 neutrons. That's where the 12 comes from. 6 protons because it's carbon. Can only be 6 protons. That's what makes it carbon. But 6 neutrons adds to the weight, so it's a total of 12, and we call that carbon 12. That's the normal form of carbon. Over 99% of carbon out there is carbon 12. But there's a small amount of carbon, little less than 1%, called carbon 13, that has 6 protons, because that's what carbon is, and 7 neutrons, so it's carbon 13. There's also a radioactive one that has 8 protons, called 8 neutrons, which is called carbon 14. But all of these have almost identical chemical behavior. They react with other chemicals exactly the same way I say nearly identical. You don't need to know the difference, but I'll tell you the difference. Because some of the atoms are bigger or smaller, they tend to move slightly slower or slightly faster, slightly slower if they're bigger in chemical reactions, but the difference is really, really tiny. All right, so isotopes. The number of neutrons can vary with different isotopes of the same element, not the protons. So you have the same number of protons because they're the same element, but different number of neutrons, which gives them a different weight and nearly identical behavior in chemical reactions. So we add those up, and that's called the mass number. It is also called, it's called the mass number because it's a number of the mass, the heavy mass particles, the protons and the neutrons. It's also called the isotope number because it tells you which isotope of it, of that element it is. Like carbon 12, carbon 13, carbon 14. 6 protons plus 6 neutrons. 6 protons plus 7 neutrons. 6 protons plus 8 neutrons will each give you different mass numbers, 12, 13, and 14. Those are also the isotope numbers. Means exactly the same thing. You're just counting up those heavy particles in the nucleus, the total number of nucleons. Another example. The most common isotope of iron is called iron 56. It has 56 nucleons in the nucleus. 26 protons because that is what makes it iron. All iron has 26 protons, but it also has 30 neutrons. So 26 plus 30 is 56. So we call this iron 56. And there are different ways to write it. You can actually write the word iron hyphen 56, or you can use the symbol for iron, Fe. It's called Fe because the ancient Romans called iron ferrum, Ferrum. They abbreviated Fe. And the 56 is always in the upper left-hand corner. That is the isotope number or the mass number. It has to be in the upper left-hand corner. Bottom left-hand corner is where you put atomic number. A lot of times we don't bother with the atomic number because we know what the atomic number is if we know what the element is. Iron is always 26. So sometimes they write 26 in the bottom, sometimes they don't. But the 56 tells you which isotope it is. It's all the information you need to tell you how many protons and how many neutrons just by looking at the symbol. So an atomic number of an atom of an element matches the number of A, protons in the nucleus, B, electrons in the neutral atom, C, both, D, neither, none. Think about that. Well, the atomic number, as we've said, is the proton number. It's always the proton number in any atom, whether it's charged or not. But this question is a little tricky. This one says of an atom, and an atom by definition, unless I say otherwise, is neutral. So while the atomic number really is just the number of protons, absolutely only the number of protons, the fact that it says an atom tells you it's neutral and that the number of protons that are positively charged must be identical to the number of electrons that are negatively charged to balance out charges, to cancel each other out. So the answer is both in this case. Kind of a trick question. I didn't write it. So the atomic number is the protons. Atoms are by definition neutral. If they're not neutral, we call them ions. But you will hear physicists refer to atoms that happen to have charge in physics as atoms all the time. They're really ions, but they'll call them atoms all the time. So I'm not going to be a stickler on this because physicists call them all atoms in almost every conversation. So when the atomic number, that is the number of protons, doesn't match the number of electrons, we typically call it an ion, at least in this class. But in real life, you'll see physicists calling everything atoms and specifying, oh, this is a charged atom, this is an uncharged atom. An atom with an atomic number of 44, remember what that means, and a mass number of 100 must have how many neutrons? 44, 56, 100, or all of the above. I'm not sure how it could be all of the above, but let's look at this. Well, think about it. The answer is 56. Remember, the atomic number is how many protons. That's 44 protons. The mass number is the protons plus the neutrons. It's all the nucleons in the nucleus, all the heavy particles. So if the protons are 44 and the protons and neutrons are 100, well, then the difference must be the number of neutrons, right? So 100, the mass number minus the atomic number is always going to be the number of neutrons. It's the remaining heavy particles. 100 minus 44 is 56. Now, be sure to distinguish these terms. Make sure you realize that nucleus, they all sound the same. Nucleus, nucleon, neutron. Nucleus means the core of the atom. In fact, it comes from a Greek word that means core, or the center of something. That's the center of the atom. The nucleus is composed of two kinds of nucleons. Protons, the positively charged ones, and neutrons, the neutral charged particles that make up the nucleus. All right. When atoms of different elements bond to one another, they make a compound. So compounds always include two different, they include atoms from two different elements. If they're made from the same element, that substance, whether it's an atom or combination of atoms, if they're all the same atom, that's called an element. That's the elemental form of that element. But once you take an atom of one element and you combine it with an atom of another element, that's called a compound. So compounds are always at least two atoms, because you have to have at least two different atoms to make them. And compounds behave completely different than the atoms that they're actually composed from, the elements that they're composed from, okay? And you can only separate them. You can't separate them by any regular physical methods of distilling or warming them up or crystallizing them. You have to break them apart by actual chemical reactions. It's the only way to break up a compound. Once that bond is formed between different atoms to make a molecule, you have to break that bond apart with energy. That's a chemical reaction. So examples, table salt, that's sodium chloride. Na is sodium, Cl is chlorine. When you put them together, it's called sodium chloride. So it's composed of sodium atoms and chlorine atoms. Sodium is usually found as single atoms. That's an element that's just made of NAs, single atom element. Chlorine is made out of Cl2. It has two atoms of chlorine. If you don't see a number next to it, it just means there's one of that element. So like H2O, H2 means there are two H's, and O, we don't have a number, so there's at least one O, or otherwise we wouldn't bother writing the O. So this means one atom of sodium in a ratio to every one atom of chlorine. It's not actually separate molecules, it's a crystal, but it means a one-to-one mixture, a one-to-one bonding of sodium and chlorine atoms. And it turns out sodium by itself is actually an incredibly dangerous reactive metal. It'll explode if you put it in water. And chlorine gas is incredibly toxic. You breathe it, you will die. And you will die a horrible death. It actually gets in your lungs and it reacts with water in your lungs and makes hydrochloric acid. It's a horrible way to go. People used this gas during World War II, World War I, and it's since been banned. But they're linked together with chemical bonds. Water is another example. Water is H2O. Two atoms of hydrogen are linked to one atom of oxygen. We don't write the one, all right? But hydrogen gas by itself is H2, and oxygen gas is O2. Those are gases. Those are totally different behavior than water, which is a liquid at room temperature. So two or more substances, and now we're talking about a substance. It could be either an element or a compound. It could be made with atoms, or it could be made with molecules, okay? So an atom is one particle of one element. A molecule is two or more particles, two or more atoms of the same or different elements. Compound, it has to be different elements. So compounds can only be molecules. They can only be made with, you have to have at least two, so therefore it's at least a molecule. And substances could be any of those. If you have more than one of those substances, we call that a mixture of substances, or just simply a mixture. So air is a mixture of nitrogen gas, N2, a mixture of oxygen with oxygen gas, O2, argon gas, a little less than 1% of our atmosphere. And then there's water vapor, there's carbon dioxide, there are chlorofluorocarbons, there are all kinds of trace gases in the air. A little bit of neon, a little bit of even tiny amounts of helium, not really much at all, make up the air. But most of it's nitrogen and oxygen. So here are some molecules. And you can see this is roughly the actual shape of the molecules. They're not really colored, obviously. Oxygen gas, two oxygen atoms linked together. There's actually a double bond between them. And then the others that are shown here are all single linkages, single bonds between the atoms. Ammonia is made with one nitrogen bound to 3 different hydrogens. Methane is carbon with 4 hydrogens. That's because carbon likes forming 4 bonds. Nitrogen likes forming 3 bonds, occasionally 4. Oxygen likes forming 2 bonds, so it either forms a double bond with itself in the first one, or 2 single bonds with hydrogens in water. And this is what water is. It's actually a little bent molecule. It's oxygen that's holding 2 different hydrogens. So if you have 2 or more atoms, whether they're the same atoms or different atoms, that's a molecule when they're linked together chemically. A chemical reaction is when you break or change the bonds. So you're either breaking old bonds, or you're forming new bonds, or you're doing both. That is a chemical reaction. And the chemical reaction involves changes of the electrons being shared between atoms. We're not going to go into that. That's chemistry. This is a physics class, so we're only going to cover this in a cursory fashion. But if you're breaking bonds and you're making bonds, that's a chemical reaction. So examples that you might be familiar with. If 6 carbon dioxide molecules, that's CO2, 1 carbon, 2 oxygens on carbon. Carbon forms a double bond to one oxygen and a double bond to the other, so it has its 4 bonds that it likes. And it's a very stable molecule, so it's tough to rip apart. You have to use very special chemicals to break it apart. Special enzymes in plants will do this. And it will, and it's a whole series of chemical reactions in photosynthesis. It's not just one chemical reaction. It's literally dozens of chemical reactions that will eventually take 6 carbon dioxides and 6 water molecules, break the bonds, reshuffle them, and build 1 glucose molecule. That's C6, 6 carbons, 12 hydrogens, 6 oxygens, so we call it C6H12O6. That's the formula for glucose. It's also the formula for a lot of other sugars, but glucose in this case. Plus 6 oxygen molecules, 6 O2s. And this is the oxygen that we breathe that comes from plants. It's the rearrangement of carbon dioxide that it takes in and water that it takes in to make sugar for itself, and oxygen that it spits out as a byproduct of plants. You can also have reactions that have nothing to do with biology. Rusting is a reaction where oxygen atoms, they could come from oxygen gas in the air or from water, combine with iron, iron Fe, to make rust. And rust is a number of different chemicals. This is one of the formula, Fe2O3. This is called ferric oxide, and it's just one version of rust. Okay, so now let's jump into something completely different with matter. Let's talk about antimatter. Now, you've probably heard of this if you've ever watched any sci-fi picture that takes place in the distant future with spaceships. And so matter is composed, most of matter, our regular matter, is composed of atoms, and atoms are composed of our standard positively charged protons, our standard neutral neutrons, and our standard negative electrons. Well, everything is flipped with antimatter. The neutrons don't flip. There are antineutrons, but it's not, they're not different because of the charge. It's other things we're not going to talk about in this course. So antimatter would have the negative particles making the nucleus and the positive particles making the cloud. It is still the protons making the nucleus, but they are negatively charged. And this is real. In fact, antiparticles have been discovered as early as 1932. That's 90 years ago. We've had real antimatter. It's not science fiction. This is science fact, okay? Positive versions of electrons called anti-electrons, we actually don't call them that usually. We call them positrons. They're positively charged electrons. The word was combined in what we call a portmanteau. That's a combined word. Positron meaning positive electron, okay, an anti-electron. So the anti-electrons are the cloud. So it's still electrons in the cloud, but they're positively charged. And the protons are still and the neutrons are still the nucleus, but the protons are now negatively charged. They have the same mass. The heavy particles are still in the middle. The protons and the neutrons are still the heavy particles, but the protons are now negatively charged, and the light particles, the electrons, are the anti-electrons. They're just positively charged. So everything's exactly the same, except the charges are switched. Other things are switched to something called spin that we're not going to get into. That's switched as well. But these particles exist, and they were discovered. The last one was the antineutron discovered in 1956. And eventually somebody was able to put these together in a laboratory, in the CERN laboratory, and I believe in Switzerland. They were able to put them together in the 1990s and see it for the first time, but they were able to actually trap it for over 10 minutes and observe it in 2010. So this was a fairly recent event in physics history. Anti-hydrogen was actually made. This is true antimatter atoms with it actually had protons and neutrons, protons and electrons. This was the simplest hydrogen atom that had no neutrons in it. So antimatter and matter particles, however, have to be kept away from each other, because if antimatter and matter finds each other, they collide with unbelievable explosion coming off from the matter, and all of matter can be turned into pure energy. And the amount of energy is based on Einstein's equation, E equals mc squared. Well, what E equals mc squared is saying is E equals m with a constant to correct for the units, because we measure mass in 1 unit, kilograms, and we measure energy in another unit, joules. So to convert those, we need a constant to convert it. Well, the constant we use is the speed of light squared, c squared. Well, the speed of light is a giant number, 300 million roughly. 300 million squared is an even more giant number. Well, if you have to multiply that giant number times the mass to get the amount of energy, a small amount of matter can be turned into a giant amount of energy. And this is why people are interested in antimatter, because the hope is that one day we could have antimatter, combine it with matter, and produce enormous amounts of energy from the annihilation of these particles. Just to give you an idea of what that means, I have a paper clip here. Try to grab one. So this is actually a pretty big paper clip. It weighs about a gram, so it's 1,000th of a kilogram. Now, if I was able to turn this paper clip into pure energy, following Einstein's equation for how much energy I'd get, the amount of energy this one paper clip, if it was turned completely into energy, would produce is enough energy to light a 100 watt incandescent light bulb, a regular light bulb, for, this is no joke, 30,000 years. So this is one of the reasons people are interested in this kind of technology. All right. So positrons, these are anti-electrons discovered in 1932. They have the same mass as an electron. They look just like an electron, except they're positively charged. And these are real. We've already been using these in technology for a long time. PET scans, you probably heard of that, but you may not know what PET stands for. Positron emission tomography. Somebody is injected with a sugar. It's a derivative of glucose called fluorodeoxyglucose. And it has a fluorine with a special isotope that actually undergoes radioactive decay and releases these anti-electrons, these positrons. And these can be detected in a big detector called a PET scanner. And so these are injected into people, this molecule with, it's basically glucose with a radioactive element on it. It's injected, and because it's glucose, it ends up going to the parts of the body that want glucose the most. Well, the parts of the body that need glucose the most are your heart, your brain, and your tumors. So your heart and your brain get lit up a lot, and that's why you can see the brain is all lit up. But tumors are lit up, clearly like wildfire, because they're burning up glucose. They're growing so fast, they're using as much sugar as they can get. They can't necessarily use this, but they think it's regular sugar, and they just pick it all up. You'll also find it down in the bladder, and that's because your body has to excrete it, so you'll end up lighting up things like your urinary tract as well, and possibly in your reproductive organs. So it's not as useful there, but you can see it's lighting up parts of the body, and you can read this caption here to see that it's lighting up a massive tumor in that's colon cancer that's invaded the liver of this poor person. All right, so antiprotons were discovered a little while later, in 1955, neutrons 1 year later, 56. So the antiprotons have exactly the same masses as regular protons, but they're negatively charged. All right, another type of matter, not antimatter. It's called dark matter. We're going to talk about dark matter and dark energy. These are particles or something of some type that nobody knows what they actually are. There are a few guesses as to the identity of what dark matter is. It's just a placeholder name until we figure out what it is. But we know there must be something that has mass that cannot be detected with telescopes that are looking at any wavelength of light. We just can't see this mass. How do we know it's there? Because we can watch galaxies spinning in such a way that we know the formulas for how fast stars within a galaxy should spin, and they're not matching what we see as far as how much matter is in the galaxy. They're matching something that has much more mass than we can actually see. At least 5 or 6 times as much mass than we can see. So we know there's something out there that's behaving like matter with mass that we just can't detect. We call this dark matter, and it represents 27% of all the matter energy. We're going to call those the same stuff of the universe. 27% of all the matter energy combined content of the universe. But we don't know what they are. It's proposed to explain that missing mass for the galaxies and how they spin, but we really don't know which particles. There have been several guesses. One or two might be right, but we really don't know. Dark energy, we know even less about. Dark energy is something that's even more bizarre. This is a theoretical proposed explanation for why the universe is expanding faster and faster. It's accelerating expansion, and that was unexpected. So how do you expand it in an accelerating way? That's going against gravity, pulling the universe back in. So this dark energy is acting like anti-gravity. We don't know if this is real. We don't know if it's some mathematical anomaly. We're missing some concept, but for now we're calling it dark energy. It's something to explain, and it seems to account for 68% of all the mass and mass energy combo content of the universe out there. And if you add these up, you get 95%. That means there's less than 5% that's the matter that we do know about. The protons, the neutrons, the electrons, the other unusual particles that make up planets and stars and people and plants and everything, okay? That only is less than 5%. It's about 4.7% of all the stuff we really think is out there. So this dark energy is proposed to explain this accelerated expansion, but we have really no clue what it is. So finding the nature of dark matter and finding the nature of dark energy, these are two of the big problems of high energy physics and particle physics and astrophysics in the world today. That's 95% of all the matter energy in the universe. But we're hoping that by the year 2050, so that's within the next 30 years or so, we'll have so much more information, because we know information skyrockets with every year. It's an exponential increase in information, and we'll probably have more information in the next 30 years than we've had in the last 400 years. So with that, we'll end the unit, and thank you very much.